Alright, this video is the combined gas law notes. So in the combined gas law, it's a combination of Boyle's, Charles, and Gay-Lussac's laws all put together, and reads out P1 V1 over T1 equals P2 V2 over T2. And of course these are referring to the initial pressure, volume, and temperature, and the final pressure, volume, and temperature. That's what the difference between the ones and the twos is. As you're working out word problems with this, you will have to use your reading comprehension skills to be able to identify which ones are the initial pressure, volume, and temperature, and which ones are the final pressure, volume, and temperature. Alright, so the good thing about the combined gas law is it doesn't require you to hold pressure, volume, or temperature constant. Like, all changes can happen to all three to solve for a new quantity. And additionally, if you do need to use one of the other gas laws, like let's say temperature or pressure or volume is held constant, you can get the others. So for example, if the temperature is held constant, then you get Boyle's law. Remember, when you hold the temperature constant, the same value is on both sides, so that value cancels out because it appears in the same place on both sides of the equation. Okay, if pressure is held constant, then you get Charles' law. And if volume is held constant, then you get Gay-Lussac's law. Alright, the most convenient way to write this is to go ahead and cross multiply. So you get the t's in the numerator, and you can see that when you do that, it reads out P1 times V1 times T2 equals P2 times V2 times T1, and that's good because it'll eliminate most of the algebra mistakes that go along with trying to solve it with the t still in the denominator. So that's what we're going to model doing when I work out these problems. Alright, so I've got a few sample problems that we'll go through here. First one says a sample of helium gas has a volume of 0.180 liters, a pressure of 0.8 atmospheres, and a temperature of 29 degrees Celsius. What is the new temperature of the gas at a volume of 90 milliliters and a pressure of 3.2 atmospheres? So one thing that would be great for us to do to start off with is to identify all of our variables here. It does give us these first three quantities together in a way such that we can tell that those are the initial temperatures and pressure and volume, and then they give us the new volume and the new pressure and ask us to solve for the new temperature. Alright, so go ahead and list out all of our data. Now, something that's really important to remember about gas law problems is that if you don't convert your temperature to Kelvin, the proportionality does not work, so you'll get the wrong answer. So make sure you add 273 to the Celsius temperature to get Kelvin. In combined gas law, it's okay to leave volume units in whatever they give you, as well as pressure units, as long as the initial and final pressure units match, and same thing for the initial and the final volume units. They cancel out, so it works out fine. When we get to ideal gas law, you will have to be a little more aware of the units, particularly on the volume. Alright, so we've listed out all those quantities. So our unknown is the second temperature, or the final temperature. We listed out all the knowns here. Now we have the ideal gas law. Let's go ahead and cross multiply. And then you can see you have P1 V1 T2 equals P2 V2 T1. In order to solve for the T2, we're going to divide both sides by P1 times V1, as you see here. And then that will tell us we need to do P2, 3.20 atmospheres, times V2, 90 milliliters, times T1 over P1, 0.8 times 180 milliliters. So once you carry out that calculation, you should get about 604 Kelvin. If you were asked to solve for the Celsius temperature, then it would just be a matter of subtracting 273 from that to get back to the Celsius temperature. Okay, so there you go. Alright, so let's pause for a moment. Alright, so I'm going to work out a few example problems. I recommend that you pause, maybe give these a try, and then work them. And then once you work them out on your own, see if you got the same thing that I got. Alright, so this combined gas law example 1, let's work our way through that. So what you should see here is let's list out our unknown. What is the temperature when the gas? So that's telling me that that's the final temperature that we're interested in. Alright, so our knowns are going to be several of those. So tells us the V1 is 675 milliliters. Tells us that the T1 is 35 degrees Celsius, so we're going to do 35 plus 273. And that will be 308 Kelvin. Right, and our P1 is 0.850 atmospheres. Alright, and they also tell us that the volume later, so our V2 is 0.315, and our P2 is 802 millimeters of mercury. Now that's a dirty trick, but got to have matching units of pressure here, so we will go through and convert to pressure. So there, recall from page 1 of your reference table, there are 760 millimeters of mercury in 1 atmosphere. So we'll go ahead and do that conversion. Alright, so we have converted our pressure so that the units of pressure match. You could have converted atmospheres to millimeters of mercury too on this side if you'd wanted to. Either one will work fine. Alright, so let's work out a plan here. So our plan, this has a change in temperature, volume, or pressure variable, so that's a combined gas law. And I'm going to go ahead and do the cross-multiplied version of that. So P1 V1 T2 equals P2 V2 T1. And we are solving for T2. So we will need to divide both sides by P1 V1, just like the other example. Alright. So what handily happens here is the P1s cancel and the V1s cancel, and that means that this is our calculation, P2 times V2 times T1 over P1 times V1. I'm going to go through and plug in all of the information from earlier in the problem for this. Oh, I noticed another issue here too. Alright, so the liters and the milliliters don't match, so I'm going to go ahead and convert the milliliters to liters. That's simple enough. There's 1,000 milliliters in a liter, so this is 0.675 liters. So we'll go ahead and do that conversion. Now let's plug in all of these values. So P2 is 1.055. By the way, I didn't round that because I don't want, I didn't round it as much because I didn't want it to affect the accuracy of my result. I'll plug in the rest. Alright, so I plugged in all the variables, and now we just need to multiply all the ones on the top, multiply everything on the bottom, divide the top by the bottom. Alright, when I carried out that calculation, I got 178 Kelvin. Now, we're not done yet because we need to get Celsius temperatures. We're going to subtract from that 273, and that'll give us a Celsius temperature, which is negative 95. So that's pretty cold. Alright, here's our second example problem. So it tells us we have a balloon with a volume of 785 milliliters, temperature is 21, gas cools to 0. What is the new volume of the balloon? So let's list off our information here. Okay, so our unknown is the new volume, or the V2, the knowns. We know that the initial volume is 785 milliliters. The initial temperature was 21 degrees Celsius plus 273 to get 294 Kelvin. And then our final temperature is going to be 0 degrees Celsius plus 273, so 273 Kelvin. Now, notice that we do have a change, so that's telling us to use combined gas law. They completely excluded pressure, so we would just assume that pressure is constant. So we'll just leave it out of the ideal, or out of the combined gas law. All right, so our plan, P1 V1 T2 equals P2 V2 T1. All right, now pressure we're just going to leave out, and then we need to solve for our V2. So this is what we're solving for. So in order to do that, we need to divide both sides by T1. All right, and the T1s over here cancel out. So the calculation that we need to do is V1 times T2 divided by T1. So let's plug those numbers in now. All right, when you do the calculation, you should get 729 milliliters, which would match our prediction from Charles' law that when you decrease the temperature, it should get smaller. Alright, so this problem asks us what is the pressure, what was the pressure of the neon gas while it's stored in a 1 liter container at negative 25 degrees Celsius. So the way this is worded to us, what we can figure out is that it's actually asking us for the initial pressure. As long as you keep the initial and the final pressures quantities separate, it still works out okay. Even if you had them backwards mathematically, you'll still get the right answer. But anyways, okay, our knowns here. So tells us that this stuff used in the sign at standard temperature and pressure, it's 15 liters. So our V2 is 15 liters. Our P2 and T2 are standard temperature and pressure. Okay, and let's see, I guess we can pick whichever pressure we want to. I'm going to do 1 atmosphere because that's really easy for standard pressure. All right, T2 is standard temperature, which is always 273 Kelvin. And then they tell us that it started out in this tank or container. It had a volume of 1 liter and a temperature of negative 25 degrees Celsius. So add 273 to that to get 298 Kelvin. All right, I'm solving for the P1, the initial pressure. And so that means I need to divide both sides by V1T2. So these will cancel out over here, and the calculation I will do is plug all my quantities in, multiply across the top, multiply across the bottom, divide the top by the bottom. Alright, when I carried out the calculation and rounded to the correct number of significant figures, I got 16. And then the units cancel out, liters, Kelvin, and leave me with atmospheres. Seems reasonable. It should be more pressurized inside of the tank. Alright, so that concludes the example problems. Thanks for watching.